my name is Lisa. Let me quickly introduce myself. I did a master's in physics at the Technical University of Berlin, where I focused on X-ray spectroscopy and the operation of a laser-produced plasma source for the generation of soft X-rays. In 2019, I came to CERN to start my PhD program. And I've been a member of the AGES collaboration at CERN's antimatter research facility, where we performed Doppler cooling of positronium, and where I was generally involved in optical methods and laser work in antimatter experiments. Then I continued as an applied fellow for 2 years at the same collaboration, and there was an overlap of the Doppler cooling project between my doctoral student contract and my fellowship. And since October, I joined the lasers and photocathodes group at CERN and started to work on a very different kind of laser, which is the Raman laser. And I'm involved in the design and construction of Raman laser prototypes, which will be today's topic. So here, a very quick introduction to lasers. Sorry to the ones who are already familiar with it, but just to bring everyone up to speed. Laser is an acronym that stands for light amplification by stimulated emission of radiation, and it basically already contains all a laser does. So the some fundamental interactions between light and matter are absorption, spontaneous emission, and stimulated emission. So when an atom absorbs a photon, a quanta of light, it goes to an excited state and can then spontaneously emit the photon again. And for spontaneous emission, the photon goes in a random direction. There is a third process called stimulated emission, where you shine a laser light into a medium that is already in an excited state, and it will stimulate the emission of the photon that was previously absorbed. And also the photon that you send in to stimulate the process will also be emitted. And this particular thing about this is that these two emitted photons, they have the exact same properties. They have the same wavelength, same phase, same polarization, and same direction. So if you now put this active medium, laser medium, between two mirrors, a resonator, and then add a pump source, which is some source that supplies energy to the active medium to bring it to the excited state, which we call population inversion, then the stimulated emission will create many photons that are sent back and forth inside the resonator, and this effect will be amplified until you have a nice laser beam that is then emitted from the resonator through a partially reflecting mirror. And laser light has some very special characteristics, which makes it so useful for many applications. The first is it is monochromatic. It has a very particular wavelength. It is coherent, so all the photons are synchronized in phase, direction, all their properties. And it is directional. It travels as a focus beam in the same direction. So as a quick introduction on where lasers are used at CERN, and in particular Raman lasers. On the left, you can see the accelerator complex of CERN, and it's most famous for the LHC and the related experiments, but there are also a number of other facilities which leverage the availability of high energy protons and the infrastructure in general. And one of these facilities is ISOLDE, the radioactive ion beam facility, where nuclides can be produced by irradiating high energetic protons from one of the pre-accelerators of the LHC, the booster, which you can see to the left of the red box. And how these radioactive nuclides are produced is by irradiating a target with high energetic protons. And then we have a lot of processes going on, like spallation, fragmentation, and fission reactions. And yeah, this is a nice opportunity to perform research with radioactive beams. There's also CERN Medicis, which supplies radioactive isotopes to research facilities for medical applications. And over the time, an abundance of different isotopes of more than 70 elements have been produced and studied. So this is ReLIS. ReLIS is the resonance ionization laser ion source, and it is part of ISOLDE. Here we use a selective ionization process to separate specific radioactive isotopes. So this ensures a high purity of these ion beams for the experiment that are otherwise hard to isolate through conventional processes. So once these isotopes are separated, they can be transferred to a variety of experiments for further research and to study their properties. And here's an example of such an experiment. And this experiment specifically has used a Raman laser to probe the transition of the atom. The atom was samarium 100. The isotope was samarium 152. And the Raman laser provided the necessary properties of the laser light that were required. It had a narrow line width to probe the transition with a high resolution. It had high stability and also was wavelength tunable in the range that was required to scan through the transition. And now I'd like to take a step back and explain what Raman lasers are and why they are so useful for research and other applications. So Raman lasers are based on the Raman effect, which is a phenomenon where photons interact with the vibrational modes of a medium. And in that process, part of the energy of the photon is absorbed by the vibrational mode, and the emitted photon is then wavelength shifted. There are two processes, Stokes, where a part of the photon's energy is transferred to the photon, and anti-Stokes, where a photon absorbs a bit of energy from an already excited phonon. And then we have the process of stimulated Raman scattering, which is a nonlinear optical effect where intense laser light interacts with the material, and thereby the Raman effect is amplified, and we can actually produce efficiently laser light with it that is wavelength shifted in comparison to the pump laser the medium is irradiated with. So one of the benefits of a Raman laser is that we have a huge wavelength versatility. So the wavelength that is emitted by the Raman medium is shifted by an amount that is defined by the so-called Raman shift, and that is specific for the type of medium that is being used. Then we can leverage that we can irradiate the medium with different pump lasers, so we can already choose a range of wavelengths according to the pump laser we irradiate it with. So then accordingly, the output wavelength will be different. So that means with Raman lasers, we can access wavelengths which are otherwise more difficult to produce or not accessible at all with conventional lasers. Another nice thing is that Raman lasers are wavelength tunable. For example, we have the crystal, and if we change the temperature of the crystal, it will change the resonator length and the refractive index of the gain medium, and thereby the wavelength will be slightly different. So if we tune the temperature of the crystal, we will tune the output wavelength. And another thing I'd like to mention is that we can also cascade the process. If we irradiate with very high intensity light, it is possible that the wavelength of the Raman shifted photon is high enough to then by itself act as a pump photon and then produce another photon of, again, a different wavelength and so on. So we have the first order Stokes, second order, third order Stokes, and that means we can produce photons of different wavelengths at the same time. Another benefit is that the output of Raman lasers it can be single frequency. That means if we shine a broadband laser onto the medium, this source will excite multiple vibrational transitions. However, the Raman medium prefers certain frequency components, and the strongest one will grow exponentially. So we convert a broadband laser input into a narrowband laser output. And this is extremely useful for certain applications like atomic clocks, which rely on the precise excitation of certain atomic transitions, for high resolution spectroscopy, for example, or also interferometry, where we need really a stable output over large ranges. So many media can be used as a Raman medium. However, there is one that was really outstanding, and that is diamond. Diamond has very outstanding thermal and optical properties, and it's extremely suitable to use it as a Raman medium. First of all, it has a large gain, which means the stimulated Raman scattering will be very efficient, and we will have high power output. The second one is it has a high damage threshold, so we can use high intensity lasers as a pump laser without destroying the crystal. Also, it has a really large spectral transparency. That means we can use very different lasers with different wavelengths to produce the Raman effect and have a large choice in different pump lasers. It's also possible to use diamond as in a monolithic configuration, which means we don't need an external resonator, but the end faces of the diamond, they will be enough to reflect the light back and forth, and we don't need an external resonator. So to sum it up, the comparison between conventional and Raman lasers. In a conventional laser, light is produced through population inversion in an active medium and stimulated emission. Whereas Raman lasers use the stimulated Raman scattering in a medium with nonlinear optical properties. For lasers, we can use pump sources that are either of optical nature. We can use flash lamps, another laser, or we can also use electricity to create the population inversion. And Raman lasers require an external laser pump source, and we have no population inversion. The output of a conventional laser is defined by the specific atomic or molecular transition in the gain medium, whereas in Raman lasers, it can be a very large range of outputs determined by the Raman shift, the transparency of the medium, the pump laser wavelength, and the temperature of the crystal. Then I'd like to present a project that was called Singular Light. And it was started in 2019 and funded by the Knowledge Transfer Group at CERN. And it was, Raman lasers have been used for many decades already. And this project was specifically to develop an add-on converter that is based on a diamond Raman laser, and that serves for converting multi-mode laser output to single mode output. And the idea was to really have this device that can be transported to different facilities and can be attached to an existing laser system to modify the output of that existing laser system to meet requirements of different applications. So this module had a really high peak power spectral density. That means the power of the input laser was compressed into a narrow frequency band. It had a high conversion efficiency, it was efficient, and the wavelength was tunable and arranged from 30 to 50 nanometers. Here were a few highlights. So in 2019, this technology was tested at Isolde Rillis, and you can see a picture where they performed calcium spectroscopy. Then 2020 and 2021 was again some tests at Rillis for different applications. In 2022, a company called Enigma came to test the technology. And then the next year, you can see that the prototype, this add-on converter, was finalized. And now the next step of the project is to miniaturize the technology and make it a standalone device. So it will also already have a pump laser integrated, and the idea is to have a compact, portable module that can be transported and used for applications. Here's a timeline of the evolution of the project. So yeah, it's been going on for many years, and there was a number of PhD and master students who have worked on this. And the project was funded by the Knowledge Transfer Group. And last year, the technology was integrated into the CVC technology portfolio. And yeah, end of last year, I joined the project. And as I said before, I have been working on different lasers. And now my task is to do the next step of the project and miniaturize the technology. I'm developing 3 different prototypes with slightly different properties. And another big goal of this project is to reduce the costs per unit to make it more attractive. Okay, again, comparison. On the one side, until now we had the add-on converter that will now be the standalone device. And you can see that also the dimensions are used by a factor of 2 to make it portable. So the first thing to reduce the costs was we cut the diamond. And this was done at a company in Switzerland, Synova. They specialize in precision laser cutting, and they have developed this technology which combines a laser with a thin water jet. And the laser will propagate inside the water jet, and through internal reflection at the air-water interface, the laser will be nicely guided along the water jet and will always stay focused on the target to be cut. So conventional lasers, they have a limited working distance. So if there are if the surface to be cut is uneven, you always have to refocus and make sure it's tightly focused. And with the laser jet, it is given by design that the laser is always nicely focused onto the surface, and that allows for very precise laser cutting. So yeah, we had one diamond that had a surface of 2 by 2 millimeters, and we cut that into 4 pieces. So in principle, we can build 4 prototypes and don't have to spend any more money on diamonds. This is the expected performance of the prototypes. As mentioned previously, there are 3 different types. The first 2 using Q-switch diode pumped solid-state lasers. They have high power, so the expected output power of the Raman laser is also going to be high. The third one is a bit different. It uses a diode laser, but on the other hand, it has a very high repetition rate and might be interesting for applications in communications. The output wavelength will be in the green and yellow for these 2 lasers. And in principle, if we use different lasers, we could, of course, reach other wavelengths as well, but it will be limited to the wavelengths mentioned in the table as the pump laser is integrated. Yeah, so the key benefits, to sum it up, will be wavelength tunable, which might be interesting for applications in spectroscopy, where you have to probe broader transitions, or for measuring the Doppler profile of a certain transition. We have scalability. So in principle, we could use the same pump laser to produce Raman output of an array of diamonds and use these, for example, for readout or reset of qubits. It's cost effective, compact, and portable. So there might be applications that are airborne on drones or LiDAR in airplanes. Yeah. First of all, I'd like to thank Eduardo Granados, who's been the driving force behind the Singular Light project since 2019. He has supervised the students working on this, and really, yeah, he's been the driving force behind all of this and the development of the technology. I'd also like to thank the colleagues that helped and supported, and the students who previously worked on this project. And of course, Lynn and Hanae. Okay, thank you for your attention.
Thank you, Lisa. I think it would be nice maybe to hear from one of the people that have been working on the same team as Lisa and are now basically outside of CERN and are thinking about application fields. And if I see correctly, then I see that Georgios is actually here. Maybe you could tell a little bit about your project using the laser.
Absolutely, Lynn. I would love it. Can you hear me well?
Yes, I can hear you well.
Excellent. First of all, Lisa, thank you for the excellent presentation. So a few words about what I'm doing or like what I did. So maybe when I was a master's student, I had the great chance to work with this amazing technology. And after a while, I graduated from university and then I said, hey, okay, entrepreneurship is the thing for me. So I knew this technology, I love this technology. So I wanted to figure out something with that. And at some point, it was not a clear thing, right? But in my university, we were really LiDAR people. And that's why it's great that, Lisa, that you mentioned the LiDAR stuff. Yeah, one day it's shown on me that the Raman laser that CERN invented is an excellent solution for the problems that the LiDAR community faces. So yeah, I launched a startup all about that, taking the miniaturizing single frequency high power laser that CERN invented and bringing it into the LiDAR world. Specifically, LightEye is all about taking this kind of LiDARs and integrating them on planes to detect turbulence early so that we can avoid all the well, highly uncomfortable and even highly dangerous stuff that happens.
Thank you. Thanks a lot. Yeah, that's a good addition to it. Then we have a question from Shivam. How to join the CERN Physics Research Group? Is there any open working or collaboration group? That's a good question. Yes. So we do collaboration with external companies, for example, or external research institutes, any kind of collaboration with external people. We do within the technology transfer group at CERN. So we call ourselves knowledge transfer, but we're a technology transfer office. And within that technology transfer office, we do, for example, R&D collaborations with external companies. We give out licenses to the technologies. We do service and consultancy agreements generally. This obviously is always good for example, companies that have a bit more time on their hand, for example, if they want to do an R&D collaboration. Now, that's not necessarily the case always for startups. Startups don't have that much time. They don't have that many resources. So because we also want to transfer this technology to startups and entrepreneurs and founders, we decided to start this program called CERN Venture Connect program. And within that program, startups are able to license technologies, for example, this technology, and commercialize those. And if there is any interest in kind of reaching out and kind of talking about what kind of application you see for the technology and what you would like to do, you can either reach out to us, so Hanae, Han, and myself, or you can also go to our website, which we can also put in the chat, so you have a better understanding as well there of how it works. Thanks a lot, Hanae. She just posted it in the chat. I hope that that makes it a little bit more clear as to how CERN collaborates and works with external companies. Um, I think if is there any other questions? We have 10 more minutes. If there's any questions, let us know. We're happy to answer them. And if you don't feel comfortable doing it here, we're also happy to answer them via email if you want to reach out to us. If not, then I wanted to take the time just really thank Lisa for her explanation. I see something more popping up in the. Yes,
Yeah.
thank you. Exactly. Also, thank you first of all, thank you, Lisa, for explaining us everything. I think kind of breaking those complex concepts down is always a bit tricky, but I think you did a great job, and I definitely understood a bit more of the laser that you're working on. And I also wanted to thank everybody in the room and everybody who joined us externally or internally. We really love to exchange with you if there is any other topic that you would like to discuss, maybe not necessarily related to the laser or related to the laser. Please feel free to drop us a message. We're happy to engage and see whether there is anything, interesting coming up that we can do together at CERN and with outside people. And yes. That was the very first session of the Deep Tech Talks. Very happy to have you all here, and we're looking forward to seeing you at the next one.